This tutorial is about creating linear graphs from nonlinear data. Imagine we have a spring to which we've applied masses of 1, 2, 5 and 10 kilograms. Those masses give us these extensions, so the first thing we're going to do is to draw a graph of the data. To find the gradient, we're going to use an inbuilt function of Excel called slope. So first of all we want the known y's, and then we want the known x's, and that gives us the slope. Next we need to find the spring rate. The spring rate is defined as newtons per metre. The gradient is the extension divided by the mass, that is millimetres per kilogram. So the first thing we need to do is invert the gradient. So that's going to equal 1 divided by the gradient, and that's the number of kilograms per millimetre of extension. And if you look at the 10 and the 32 there, 10 over 32 is roughly the same as 1 over 3, which is what we've got here. So that is kilograms per millimetre. The next thing we need to do is to turn that into newtons by multiplying by 9.81. And that is the number of newtons per millimetre, and then finally we need to multiply that by 1000 to turn it into newtons per metre, and that's the spring rate of this spring. What we're going to do is drop a mass from the top of the Leaning Tower of Pisa and measure the distance it's fallen over time. So we've got a series of times and a series of distances. So let's start by graphing these. And as you can see, this is definitely not linear. Newton's law states that the distance is equal to the initial velocity times the time plus a half the acceleration times t squared. The ball was stationary at time equals 0, so the ut term goes to 0. The distance is now equal to a half at squared. So instead of plotting distance against time, let's plot distance against time squared. So what I'm going to do is move the distance down 1, and I'm going to say that this square is equal to that times itself, which is obviously 0. Copy these across here. So now I've got time squared versus distance. So if I plot a graph of those, this time the graph is linear. We can find the gradient. And remember, it was a half at squared, so g, the acceleration due to gravity, is equal to this value times 2. And that's in meters per second squared. For our third example, we're going to look at the rate of cooling of a hot object. We've measured the temperature for a given series of time. Time is the independent variable and temperature is the dependent variable. So let's start by drawing a graph. Clearly that is not a linear graph, so we need to think about the equation. So the temperature at time t is equal to a constant times e to the power of minus kt. The e to the minus kt suggests we take natural logarithms of both sides. So what we'll get is the log of t is equal to log of a minus kt. So now we need to plot the log of the temperature against t. So we're going to have that is equal to the log of that cell, and then we'll copy those. So now we want another graph of time versus log of temperature. So we have a linear relationship between log of temperature and time. So we can find the gradient, and that's equal to slope which is minus 5.4. So K is equal to in summary, therefore, we've looked at three equations. The first one was linear, and we were able to determine the spring rate. The second one was quadratic, and by plotting distance against time squared, we were able to calculate the acceleration due to gravity. And on the third one, we had an exponential relationship, and by plotting the log of temperature, we were able to find the rate of cooling.